By anonymizing your data with Truata and leveraging our machine learning analytics, you can easily build a model on your entire customer data, unconsented as well as consented. Let's see an example where we build a churn prediction model for a telecom operator using a two-class classification workflow. We launch this workflow by logging into the web portal. Each page is a step in the workflow that guides you in building your required prediction model and gives you great flexibility in configuring and pre-processing the data and machine learning algorithms. The guide panel on the right contains technical documentation and will help you in making informed decisions. The progress we make in the current workflow is indicated by the progress bar. We log in by entering our username and password and our email ID to receive a notification after completion of certain steps in the workflow, as they may require significant execution time due to the amount of data. In our next step, you can see a list of tables in your data source, along with a schema that are accessible to you. Then you can define the query to extract the precise data that is needed to build your model. In our case, it will be the entire customer retention table. This table contains information on various attributes regarding telecom customer data, such as their product preferences, tenure, and spend, as well as an indicator of whether or not that customer has churned. This step also gives you the option to view useful statistics related to your results set and its synthetic version. You can skip statistics to save processing time if you already know the data well. In the next step, if the option was selected, you can see useful statistics for all the fields in your results set, nominal and numerical. Typically, in a machine learning experience at this stage, you might want to explore or preview parts of the data itself, but even previewing a small amount or individual data fields creates a privacy risk. Truata has created a preview function which shows a synthetically generated subset of data. This synthetic data has the characteristics of your results set at a field level, but with privacy risk reduced to an insignificant level. Next, you can select the target field that you want to predict. In our case, it's churn. 0 churn, 1 no churn. Additionally, you can opt to view relevance of fields in your dataset with the target. At this stage, we automatically partition the data internally into train and test set. We do pre-processing on the data before calculating relevance score of each field with the target. We can choose to remove outliers, handle missing values, normalize the data, and convert categorical fields to numerical, such as one-hot encoding. These are sample pre-processing steps that we currently support. Additionally, frequently used pre-processing activities can be applied, and it is also worth noting that as each client gets their own instance of the workflow, we can have customized capabilities at every step. Next, if Outlier Treatment was selected, you can configure how you want to handle outliers, such as you may choose to replace them with mean median or exclude the entire rows. Similarly, missing values can be replaced with average or most frequent values of that field, or a 0 or a NA based on the field type, such as nominal or numerical. You can do min-max or z-score normalization, which allows you to have all your features within similar ranges and helps to speed up model training and makes optimization easier. At this stage, under the hood, data is being pre-processed and relevance is calculated with the target that would help in filtering the irrelevant fields. We can see the relevance calculation for each field in the below table. Various tests, such as missing and constant value check, noise test, are computed for each field, along with correlation with the target. All these scores are then combined as overall relevance score, which indicates how much each field will help in predicting the target. Hence, you may choose to filter fields that have less relevance with the target, either using the slider or manually, as they might be of little help to your prediction model, or rather add noise during prediction. This also helps to avoid the issue of dimensionality and speed up the model training process. Next, we will do some feature engineering. model selection, and hyperparameter tuning on our chosen models. We generate additional features by computing them using following techniques such as simple transformation, dimensionality reduction, cluster distance transformation, and feature combination. Descriptions of these are all displayed in our guide panel on the right. The complexity defines how aggressive feature engineering should be performed. For example, if it's high, then we do wider exploration of various newly computed feature combinations along with original features while training. Now, depending on the machine learning task, a list of suitable algorithms will be shown. Since we are doing classification, it shows us these 5 algorithms. For each selected model, you can fine-tune the hyperparameters. This will perform grid search and report best parameters for each model. Usually, the larger the range you select, the better the hyperparameter optimization results would be. However, increasing the range can also significantly increase the processing time required. Truata's machine learning analytics uses Spark to run our machine learning jobs in distributed framework and will scale elastically. But even still, these jobs can take some time to execute. To mitigate this, our analytics solution has a useful feature which will email you a notification when the jobs are complete. This email will contain a link to the next step in the process. After setting these hyperparameters, model training kicks off. Once this training process is done, we can see the model results for each algorithm. We can compare all selected models by accuracy, area under the curve, or training and execution time for a single prediction. From the first chart, by comparing AUC values, we can see that random forest model performs the best. Also, average training time for each algorithm and prediction time per sample can be compared. This can be vital if you want to productionize the models. The ROC curve makes it easier to compare performance of all these models. If we have lost track, we have a table summarizing feature importance for each model, showcasing features that have contributed the most to the classification. These will be helpful in establishing what customer attributes are most likely to either drive or reduce churn, giving us helpful indicators for churn prevention campaigns. This also shows best hyperparameter values, AUC, and additional metrics. Finally, we have the option to download the best model across each algorithm, which can then be imported by the user into any in-house application for execution on consented data. Contact Truata for more information or to request a demo.